Okay, hi guys, welcome back. So this is the final part in this chapter 1, which is catalyst deactivation, right? So the part of deriving the rate law is already finished. I have covered until part 6. So this part will discuss solely on the catalyst deactivation, right? Okay, so what is catalyst deactivation? It is also called catalyst decay. So, catalyst deactivation is actually a loss of catalytic activity. Okay, so catalyst activity is defined by AT equals to RA at time t at any time over RA at time 0. Okay, so if your catalyst is is 100% active, your AT will equals to 1. Okay, but somehow due to catalyst decay, your AT will not become 1. Okay, so all right, so later we will see how this catalyst activity will be insert into your reaction rate to see the effect of catalyst deactivation on your reaction rate. Okay, so the rate of catalyst decay or RD can be expressed as, okay, it's just similar to the overall rate of reaction, but this time around it is dEA over dt, meaning that the differential in your catalyst activity over time. Okay, so it's as a function of this is your AT, and then your KD is like your reaction rate constant, but this one is for uh, decay rate constant, we call it, which is also related to temperature as what Arrhenius equation. Okay, so as a function of CA, CB depends on your reactant and your product. So for first order, you will have your PA will become A, and second order decay, your PA become A squared. Right. So let's go to the next slide. Okay, this is types of catalyst decay. Okay, whether it is caused by thermal or mechanical or chemical. Okay. So these 6 ways how to kill your catalyst, and the subsequent of this is having a catalyst decay. So the first one is by poisonate. So this is what we call it um, chemical deactivation. Okay, plug with carbon or coke. So this is mechanical. So it's like your the carbon from the reaction, it will plug the pores of the catalyst. By sintering, this is what we call it through thermal activity, where at higher temperature, it will decay the catalyst. Vaporize or volatilize it, it will through chemical or thermal, and then form inactive phases. So when it forms inactive phases, okay, it subsequently will affect the catalyst decay, where some of the catalyst active site will be covered by these inactive phases. Okay, so this is due to the chemical or thermal treatment. And then crush or grind or erode it, so your catalyst will have mechanical deactivation. Okay, the next one is example of the catalyst decay that we have. So the first one is non-poison catalyst surface. This is like the typical, this is a fresh catalyst. So when it is poison, okay, so remember this one, just now we call it poison the first way. So having silicon oxide, so you see the blue color is actually covering the active site. The active site is actually in the blue color. That is the metal part of it. Okay, so this part, okay, if you look here, this is the catalyst support, and then the green color is actually your metal part. So poisoning, you will see sulfur. Sulfur is very known as element that will that will easily poisoning your catalyst. Okay, so the sulfur will poison, and then will block the active site of your catalyst. Okay, the C part is your sintering of the active metal particle. This will reduce the catalyst active site. So supposed to be dispersed throughout the support, and then when it being sintered, it is migrate. Okay, and the particle size will grow. This is not good. Okay, and then sintering also will make an encapsulation of active metal, so it will you encapsulate your active phase, so your reactant cannot go in there, right? So these are some of example for catalyst decay, right? So this is time scale of the deactivation. Okay, let's go for example how catalyst decay will affect in batch reactor. Okay, so this one is actually more or less your example in your textbook in example 10.5. Okay, consider a reaction of A to B. Okay, so the reaction information given. Okay, isothermal. Okay, liquid phase, important, batch reactor, and then catalyst due to decaying order. So decaying order is second order. Alright, so initially the W is 20 kg. This is the reaction rate constant. This is decay rate constant. And this is V, volume 200 liter. They want you to determine X at T to 2 hours. Alright, so how are we going to solve that? Well, the first one, we need to derive the equation. Okay, so you should know that this is the design equation for batch reactor, right? Okay, right. So the reaction rate law, this is what you learned last time in reaction 1. Ra is equals to Kca. Okay, but now you have these terms At. So last time it was At equals to 1. That's why you don't have it in the equation. But now since we know already the catalyst will decay, you need to incorporate the activity, the catalyst activity into the equation. Okay, so if we look back, okay, this is a first order reaction. Okay, but the decay is second order. That's why it is first order. Okay, first order. Okay, you assume it is elementary. But the decay law, okay, is actually second order. Okay, so I will tell you where to get this one. Okay, so At, okay, so from your textbook, okay, the equation is actually Rd equals to KdA. N, but in this case, N equals to 2, right? So this one is equals to negative dA over dt. Then you integrate it, so it will become At equals to 1 over 1 plus K dt. So this equation is actually in your textbook, page 10, page 710, equation 10.97, and also because I combine it 10.98. So please highlight this equation in your textbook. Okay, right. So when you have this equation, you will incorporate this into this part. Okay, right. So for stoichiometric, this is like the typical one you learn in CRE1. Okay, so next is to solve this equation, right? The batch reactor design equation. That's why it becomes this. Okay, so ds dt W over V is this one, right? So when you already incorporate, this is for one. This is actually for your At just now. Okay, right? So you insert the equation the equation for 80 and you derive, you what we call it, you differentiate, you integrate both equation, then you will end up with this equation. Okay, so insert all those information given. W equals to 20, the K prime also given, V 200 liter, KD is also given. Right, so finally your X is only remain 0.136. Okay, so if you look here just now, okay, so KD is actually based on this one, also follow Arrhenius equation. Okay, so this is equation you can find, let's say different, let's say you want to find different KD at different T, you use equation, Arrhenius equation in 10-100 in your textbook. Okay, but this question asks you at the same temperature, so you don't have to find a new T, a new K, right? So you can also use this, the one in the red color, this column is for your AT. So just now is for a linear, so your AT is equals to 1 minus beta naught is actually your KD. Okay, so similars go by the rest, so you just choose from here. Okay, hyperbolic is this one, hyperbolic is square, so just now it's actually this one is A. Okay, so it's actually, if you rearrange it back, A equals to 1 over 1 plus beta square T, the one that you use. So beta is actually your AD. Okay, so that's why you use this just now, so you don't have to derive, just refer to this column. So for moving back reactor, it's just the same, giving you this equation. This is example in your textbook. Okay, so example 10.7. So moving back reactor is like a packed back reactor, but this part is moving. That's why they have that delta Z, right? So you go through this example, this question. I will go fast, and you may ask me in the class through the WhatsApp. Right, but bear in mind this one is actually the reactor contains 22 kilogram of catalyst that move through the reactor, okay, at rate of 10 kilogram per minute, and this is your 30 mole per minute is your FA naught, and concentration CA naught. Okay, you want to define the conversion, so you go to this part. So it is like a PBR equation, right? Okay, the rate law is actually a second order. Okay, although it looks like first order, but somewhere in the text saying that it is second order. So read carefully. So it's second order, but the decay law is first order decay law. Okay, so again, this is actually the initial equation. Okay, so using the equation in 10.124, so you need to highlight this. Okay, 10.124. Okay, and then integrating it, you integrate this thing, integrate, so it will become this one. Okay, so when you already produce this equation, you will insert this into this part. Okay, and then CA, this is normal stoichiometric. Okay, solve for this one. Okay, and then you integrate dW with dW, X with dX. Okay, so you will get final is 55%, right? So I think you need to further read on the textbook, okay, especially on how becoming this one. Okay, so this one, this part is being described, okay, in your textbook. So you may, okay, so this is by equation 10.124, okay, and then this one is integrating. Okay, so you should highlight this equation. Okay, right. So I think that's all for this chapter. So that's all. End of this chapter. Bye guys.